In this video, we'll discuss the extreme value of a given function because in many situations, given a function, we want to get the place, which means where, right? The function reach the maximum value or minimum value. For example, if you are given a cost function and you want to minimize the cost, so you want to get some parameters, make the function reach the minimum value, absolute minimum value. And for example, if you are given a profit function, you are looking for a number, right, or some more than one numbers, if your function has more than one variables, at which the function reach the absolute maximum value. You want to maximize your profit and get and also minimize your cost. There are many other similar applications, right? Giving a function of things, you want to get the extreme value, either maximum or minimum, right? Before we do anything, let's try to write down a definition for that. So what's the real meaning of being a maximum or minimum, right? What's the actual meaning? So we're given a function. So let f be a function, and D here be the domain of f, right? And we take a number in the domain, take a C here inside D, right? So what's the meaning of f of C to be absolute, to be Z, right? There might be more than one place you have Z absolute maximum value, right? So definition, the first one here is f of C is the absolute maximum value of f on D. Now, what's the meaning of that? So that means for any other function value, the other value is always smaller, right? Which means if what f of C here is greater or equal to f of x for any x inside D, right? So f of C, no matter which other x value you choose, f of x is smaller or equal to, right? Let's see our second definition, very similar one, right? F of C here is the absolute minimum value of f on D. If what happens, if f of C is a minimum, right? F of C is less or equal to f of x for any x inside D, right? So let's try to sketch an example, try to identify the absolute maximum, absolute minimum, right? So let's say this example. This is our y-axis. This is our x-axis, right? We have a function look like this, right? I can see that there are some special points. This function is getting larger and larger negatively with our lower bound. So this is our function y equal to f of x. Now you can see that this function for sure has, this is the example, right? In this example, f has no absolute minimum because the function has no lower bound, right? And also you can see that absolute maximum happens at here, right? Let's call that A here. So f of A here is the absolute maximum of f on D, and D is from 0 to some number, right? And there are other special points. For example, here, let's call that point to be B. And B is not 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 the absolute minimum because there are some function value less than B. But if you look close to B, that's a minimum around B, right? So this is where the absolute minimum could happen, right? So this is like a local minimum. So that's some critical points we have to pick up. So we give a name for that. F of B is not the absolute minimum value of F, but it has some nice properties and we want to catch, right? And it is called a local minimum minimum value of f, right? So we want to identify the absolute maximum minimum values, but we just in the end we need to get all the local maximum minimum values because using derivatives we can capture them. And then we can compare all of them to get which one is the biggest one, greatest one, which one is the smallest one. We will get our absolute maximum, absolute minimum, right? So that's our goal. So let's try to write down a definition for the local version of absolute maximum value and absolute minimum value. And 3 here, we call that f of c is a local maximum value of f just locally, right? If f of c is greater or equal to f of x when x is near c, right? Intuitively just near c. You have a small you can call that neighborhood of C. In this small neighborhood, in this case, something like this, in this small neighborhood, function value is always less or equal to f of C, right? And the last definition, very similar one, we get, if you say that f of C is a local minimum value of f if f of c is less or equal to f of x when what happens? X is near c, right? So this, as I just mentioned, our goal here is to identify the absolute maximum value, absolute minimum value, but we cannot do that directly using derivatives. Using derivatives, we can only identify the local maximum, local minimum. We will give a condition for that. And then if you get all the local maximum, all the local minimum, right, local extreme values, the biggest one will be the absolute maximum, right? And sometimes we have to consider the boundary point. The boundary point is something else we have to capture, but that's basically the idea of finding all the extreme values, right? Theorem. So first condition here is first question here is what kind of function has absolute extreme values, right? Some function for sure, the picture here we have has absolute maximum, but do not have absolute minimum, right? So we want to first get a sufficient condition such that the function has both, right? So we can find them, right? So we are the first answer here is first question here is ask what kind of function possess the absolute maximum value and absolute minimum value. So when you try to find them, you can use this theorem to guarantee the function you are investigating do have this absolute extreme values, right? So this result is called the extreme value theorem. Basically, give you a sufficient condition such that the function has both absolute maximum value and absolute minimum value. So if f, right, our function is good, you can imagine that the function has extreme value only if the function behaves nice, right? We have a good condition for that, which the function is continuous on a closed interval. Just closed means this interval contains the boundary point, right? So this both boundary points are included. We have from A to B. So that's our bounded closed interval, right? They should also be bounded. A, B are finite numbers. A, B cannot be infinity or negative infinity. Then what happens here is then f attains the absolute maximum value. We call that f of c, and the absolute minimum value. We call that f of d for some c d inside our closed and bounded interval. So which means this is good, right? If you have a continuous function, you have a closed interval, you can identify the absolute maximum and the absolute minimum value of this function, right? They exist. So sketch an easy illustration. So if you have a closed and a bounded interval, a to b, you have a crazy function, but this function is continuous. Okay, that's a good example. I can see that the function reach the minimum value at here and also maximum value at b, right? Could be a local minimum, which is also the absolute minimum value. Could happen at the boundaries, right? The boundary point a and b, the terminal point of interval, right? So that's an example we have here. So this is our absolute minimum value. This is our absolute maximum value.